to bring your bio,
Yeah.
and you can go. After you.
Thanks, Roland. As Roland said, I'm in Singapore next week, so if anybody is interested to meet, I'm happy to chat to discuss research and collaborations and so on. As Roland said, I'm at the University of Edinburgh. My research has been mainly, as the title of this talk indicates, at the intersection of machine learning and reasoning. And this is obviously an interesting topic right now for a number of reasons, including what people are trying out with large language models. But there's a very old history of where these two areas meet. So what I thought I would do is maybe give you some ideas on the dimensions of this intersection. I don't have too much detailed technical material in the talk anyway, so but nonetheless, there are one or two technical points. So if you do have questions, feel free to interrupt me or wait for the questions at the very end. That's fine too. Um, my lab at the University of Edinburgh carries out, a continued research at this intersection. So if you're curious to see the kind of work you do, you could head over to our website. And if you just Google my name or the University of Edinburgh, you should be able to find us, and you could have a look at the kinds of things we're doing. So this is a small demonstration of some of the topics we get into. So what I thought I would do is, if it's okay, Roland, I'd start off. What I thought I would do is I'll give you a quick tour of what this really looks like. This is an old topic on where exactly reasoning and learning come together. And as the title indicates, it goes back to the Greek philosopher Aristotle. And now we are all the way in neural networks. And again, with neural networks, we see that reasoning continues to play a very important role. So let me get started. If you can't hear me or if something feels off, please interrupt me. So here's the agenda for today's talk. I'll briefly go over the history. I should note that some of these kind of survey material, including the nature of the talk, has appeared in a couple of book chapters that are available online. So there's one at the bottom. So there are two books edited by Pascal Hitzler and his collaborators. You could have a look at them, and they include a small survey on the history of logic and learning. So I'll briefly go over the history. I'll talk about various ways in which logic and learning come together. I'll talk about one particular technical idea in a little more detail. I think this is quite interesting and useful for the future of AI. And then I'll conclude. And broadly, the way to think about this is that the idea that we need to think about reasoning and learning is actually a foundational topic, including in cognitive science, because humans seem to do this very well. Humans certainly learn things, but we also reason about the things we have in mind. So, for instance, if I tell you that I don't know the phone number of a certain person, then if you know the phone number, you'd automatically infer that obviously I'm looking for this information and you'd give it to me. Right. So there's quite a bit of reasoning. There's a social aspect in reasoning as well. Philosophers have also talked about, the combination of reasoning and learning quite a bit. And of course, in AI, this is an age-old topic on how we can bring reasoning and learning together. What it looks like mathematically often is that in the logical side, you're often trying to deduce some facts. So you might have a knowledge-based delta, okay? And you use some sort of logical machinery, such as proof theory, to conclude that phi follows from delta. And often it's the case that phi is not in delta, right? So it's not explicitly mentioned. It's that there are some other things mentioned, and you apply chains of inference and then essentially derive phi. Okay. In a first order setting, it becomes more interesting because delta can involve quantifiers. So, for instance, you can say every person is a smoker, has a friend. Okay. So this might be some way for you to capture that smoking happens to be a social project, so to speak. Now, you could contrast this with reasoning. Sorry, you could contrast this with learning. where what happens is that you have a bunch of data points, and the objective here is that you are trying to induce some sort of average or statistical pattern from these data points. Okay, so you want to obtain d hat from d1 to dn. Conversely, you might think about some distribution theta, and you're trying to sample from this distribution. So this distribution captures how exactly your data points are set up in the space, which points are more likely, which points are less likely. So when you sample from this distribution, you basically get elements of this data set. More representative ones will appear more frequently, and the ones that are less representative will appear less frequently. So it's a very, obviously interesting idea on both fronts. And to some extent, we can see that there is a need to combine both of these aspects. Okay. And this goes back to the title. I'm not going to go into too much detail, but many prominent philosophers and logicians, such as Aristotle, David Hume, Rudolf Carnap, have looked into this topic. And in the more modern AI circles, we often come to this paradigm of trying to bridge logic, probability theory, and machine learning. There are many different flavors. Okay, you may have come across these in your class, but if you haven't, it's surely worth a lookup. One classical paradigm is called a statistical relational AI, so it's called star AI, where you have statistics, relations, and AI. That's where the name comes from. NESI is abbreviation for neurosymbolic AI. This is a more recent paradigm where you combine deep learning and symbolic information in various forms. And robotics, of course, is a classic paradigm going back to the 1970s, where you had to deal with low-level perception data, but also high-level reasoning and planning. So robotics has always been an embodiment of reasoning and learning. As you go deeper into the topic, there are more involved topics you can get into. One topic is this idea of abstraction. It's the idea that information needs to be somehow segmented and predicated depending on the context and the level at which it's being used. So the data that is being read by the robot is not the same data that ideally goes into the user of the robot. He needs high level information. Causality is an important topic, which tells you how certain events correspond to certain observations. This becomes essential in medical science. For instance, if you want to know things like does smoking cause cancer? Ultimately, I would say the most broadest kind of regime we can look at in this space is this idea that there are constraints surrounding the natural world, right? So there are physical constraints of the laws of gravity, there are laws of velocity and motion, and all of these somehow have to somehow shape your data. And embodying constraints in a machine learning pipeline is one of the holy grails of reasoning and learning. You might have also come across this very popular dichotomy used in cognitive science and economics, this idea of system one and system two thinking, the idea that most human thinking can roughly be divided into two camps. Some of this thinking is reactive. So if someone brings a source of fire towards you, you react and you move away. But some things are deliberative. For instance, if you're figuring out what might be the best meal to have now, so that you have a light dinner. This involves some amount of more deliberative reasoning. So that's a different kind of system thinking. So this is different ways in which the paradigm of logic and learning come together. Any questions? Feel free to stop me. If I'm going too fast, I can stop and explain something else, but let me know one way or another. So I think I may not be able to see the chat, but Roland can speak up in case you guys have any questions. So broadly, there are a couple of key dimensions in this whole paradigm. Okay, so when we think about how logic and learning come together, we want to somehow think about these three dimensions. One dimension is how much prior knowledge do we need? So how much information do we need to get from experts to get a very effective and efficient system? Okay, how much do we acquire? and how much do we assume that the expert has provided? So these are questions that come up, design questions that come up when you build a system that integrates reasoning and learning. And finally, which parts need to be generalized and which parts need to be taken as something that is axiomatic, something that is basic and cannot be changed. Okay. Again, these questions come up when you think about, more involved questions about AI design and what does cognition in AI look like. But as I said, at a more coarser level, we might see that, machine learning and symbolic logic have two distinct fields, but there is quite a bit that we can say at the intersection. Here is a slightly more granular look at what's happening. I'll explain some of these things in this Venn diagram going from left to right. So the left circle is logic. Okay, so here typically you deal with truth that is false or true. Okay, so this is classically called binary truth values. But nowadays you have many systems where the truth is not 0 and 1, but it can be a real number. And this actually becomes more important when we go into neural systems, because neural systems typically don't deal with binary outputs. Okay, the classical tasks that we do with logic is deduction, which as I mentioned, you're deducing some fact given a knowledge base, but there's also something called as abduction. Abduction is where you have some observations and you're trying to conclude what hypothesis might explain these observations. So if you're familiar with Sherlock Holmes by Arthur Conan Doyle, he often says deduction in the stories, but he's actually doing abduction because he has some observations and he's coming up with a hypothesis that best explains the observations. So one thing that people may be less familiar with is that even in the logic landscape, there is quite a bit of accounts on induction. Okay, so induction is where you try to learn things and you can learn in a logical paradigm. So there are things like inductive logic programming. This is what I've written in the red in the very bottom. Inductive logic programming and statistical relational learning. Both of these are induction paradigms with a logical basis. Okay. Now, if you shift over to the right circle, the bigger circle, you have machine learning, where classically you're doing things like classification or regression or sampling, right? These are the classical things. But obviously, once you start applying any of these ideas to learning logical artifacts, then you're back at that intersection of the left and the right big circles, okay? Within machine learning, you have deep learning, of course. And in deep learning, what's specifically happening is that you're often sampling from a distribution parameterized by theta. Okay, theta is basically a placeholder for however you construct a neural network. You might be using hyperparameters, you might be using architectures of a certain type. And then once you construct and train this network, you sample from this network. And that's what gives you the prediction. So if you really look at the intersection of the smaller circle and the logic circle, then you really have neurosymbolic AI sitting at the intersection of these two. Okay. So neurosymbolic AI is basically a more recent development, although there are some historical trends going back to the 90s. It's a more recent development. The modern variation uses the best of deep learning and tries to inherit or take on something from logic and apply it there for various reasons. And I'll give you a couple of examples in this talk. So three key themes, okay? This is a way for you to think about how logic and learning come together. And I've kind of hinted at it as I've talked. So one thing is logic versus learning. Now, as I said, logic and learning to a large extent seem to be solving complementary problems. But you might think about some clever ways in which you could use logic-based reasoners for machine learning and likewise use machine learning based systems for logic. So an example, of course, a more recent example is large language models, which try to use machine learning to somehow proxy how reasoning works, and not always very reliably, but nonetheless, that's an example of using learning systems for doing logic. The second key theme would be to use machine learning primarily in service of logic. Okay, so in logic, we construct these knowledge bases or theories, and often you might ask for some help in learning these theories. And this happens in areas such as program induction in computer science, where you're trying to learn a program from data so that you don't have to write the program. And this is an example where learning is helping. A GitHub Copilot is potentially another example where learning is being used in the construction of the program. So you could see this as learning for logic. And finally, you have logic for learning, where you're using logic to enhance the capabilities of machine learning systems. One thing I won't talk about in too much detail in this talk is this kind of dichotomy or even misconception that people have that logic is primarily for discrete things and learning is primarily for continuous things. Now, the reason this dichotomy comes up is that, of course, logic, as I said, classically deals with binary truth values. So people often think of it as discrete. And classically, if you think about a neural network, to differentiate, you need a continuous space. So classically, people would say machine learning systems and deep learning in particular only deal with continuous data and continuous manifolds. And the thing is that there is quite a bit of things to be said, quite a bit of area and development to be said at the intersection of these two. I won't go into this, but the book chapters that I mentioned at the start of the slide deck, you could go and check them out, and there is a discussion on the discrete versus continuous there. Any questions before I go on to some of these key themes?
Any questions? Vaishak, there's just one, maybe not a theme, but another dimension may be complexity. What can we do, what can't we do, how difficult it is to do it, and so forth.
Yeah.
Because learning and logic, I guess they have different natures.
Yeah, no, you're absolutely right. The complexity issue is certainly a factor. I suppose you could think of them as a separate dimension here, but the way I interpreted the complexity dimension is to then look at the complexity that arises in each of these individual teams, because obviously, if you do learning for logic, it doesn't mean that you can learn everything, right? So you can't learn, it's not easy to learn second order formulas, for instance. So there's a complexity factor that's coming in. In fact, even in the reasoning aspect, the very first key theme, we'll see that even using logic-based solvers for learning is sharply hard. So, each of these dimensions have various complexity aspects, but I certainly think you're right that there's no harm in also mentioning the complexity aspect kind of glides through each of these themes, right?
Also, I would say that maybe for the popular learning kinds of papers, they gloss over all this complexity issue.
Hmm.
I mean, they don't even, the word does not even appear in the
That's
papers.
right. That's right. Yeah. Absolutely right. And this is, I mean, in a way, this has led to these kind of surprising theory papers at ICML and NeurIPS, where, people have said, well, what is the expressiveness of things like graph neural networks? Because it turns out that graph neural networks do very well with certain tasks, but don't do so well in other tasks. So what's happening? What is the expressiveness? Or what's the complexity of trying to learn in the neural network space? And there are all of these theoretical papers that, as you say, are kind of being published in these venues, but they are a separate beast, and most papers just don't talk about it. They just assume that you train a neural network and the neural network is a given thing. And maybe they might talk about the number of parameters or the number of data points, but not really formal complexity at all. So this is absolutely an issue, right? I mean, theoreticians are also to some extent trying to wrap their heads around this because they're trying to figure out how much of the classical notions apply realistically to what people are able to do with machine learning. So how is that machine learning systems sometimes do some things very well, which we would in principle consider somewhat hard. So yeah, very interesting, I think, dimension to explore. Can I go ahead, Ronald?
Yes, go ahead. I was just muted.
Oh, okay, good. Good. So let's start with the first one, logic versus learning. And given Roland's question, I might try to bring up the issues of complexity wherever it occurs to me. What's happening in this first line of thinking is what can we say about comparing computational strategies, okay, between logic and learning? And the way to think about it is rather than think about machine learning, which is a much broader thing, which includes prediction and regression. Let's go back to the fundamental problem of probabilistic reasoning, which underlies inference. Okay. So the thing to note here is that I will talk about a simple programming language called Problog. Maybe you've heard of it, maybe you haven't. Presumably, many of you have at least heard of Prolog, where Prolog is a way to deal with clausal rules. Okay, so for instance, if you ignore the point 0.5 and point 0.6 here, what's it basically saying is heads 1 is true, heads 2 is true, and 2 heads is true when both heads 1 and heads 2 is true. Okay, so what I'm trying to model here is 2 coin tosses, but by adding probabilities now, I can provide some kind of uncertainty to coin toss. I can add a bias. Okay, so basically, I'm saying the first coin toss is fair. You could get heads or tails with equal likelihood, where the second one is unfair. And there's a 60% chance that head falls and 40% that it's tails. And so two heads now defined this way is basically capturing a mixture distribution. Okay, so two heads is true only when both of the heads comes out true. So obviously, if you query two heads, it's going to be 0.5 times 0.6. Okay, so this looks like a simple programming language. Why bother with this? The idea is that you can use this programming language to construct very complex probabilistic models. Here's a slightly more complicated example, but still not that complicated. You could write many lines of such programming languages. This is an example for Bayesian network, which again, you may have seen in some of your introductory AI courses. It's basically saying that either a burglary or an earthquake could trigger an alarm. And when the alarm goes off, it's going to lead to both John and Mary calling. Okay. Now it turns out that this Bayesian network can also be written as a Problog program, like the one I described a while. But more interestingly, it can also be written down in propositional logic with some weights. Okay. So this might seem a bit strange, and it turns out, in fact, that a whole bunch of different probabilistic representations, from Bayesian networks to Markov networks to what are these things called probabilistic databases, they all can be converted to a single task based on satisfiability. Okay, satisfiability, as you know, is you have a propositional formula, and the task is to find an assignment to all the propositional variables. Now, there is an extension of the classical satisfiability question, where rather than computing just one assignment, you compute all the assignments, okay? And if you compute all the assignments, you call this model counting, because you're counting the number of models. And there's yet another extension to model counting, where rather than simply count all the models, you also assign weights to each of the models. And it turns out Bayesian network inference has a very direct translation to weighted model counting. It looks a bit like this. Okay, so basically you have a Bayesian network phi, and you take down the Bayesian network and the probabilities of the Bayesian network, and you encode this in terms of this weight function W. Okay, and you can compute the probability of some query given some evidence in terms of weighted model counting. So essentially, you can use a SAT solver to compute inference in Bayesian networks. Now, going back to the complexity question that Roland mentioned, the trouble here is that, as you know, SAT solving is NP complete, and model counting turns out to be the counting version of NP. So it's a sharp P hard, okay? But there's nothing being lost here, because as it turns out, Bayesian inference classically, if it's done exactly, is also sharp P hard. So we're not making anything worse. In fact, we might be making things a lot better, because with this approach to capturing inference, we can encode a lot of hard constraints. So for instance, in this example, you might have a constraint that says that John would only call if Mary doesn't call, right? So for instance, let's say John and Mary are a couple living in the same house, so it's unlikely that they would both call at the same time. So if you wanted to encode this constraint, it's a bit tricky to do this in the Bayesian network, whereas in the logical setting, you can simply impose a constraint that John calling is only true if Mary doesn't call, and vice versa. Okay. So essentially with weighted model counting, you get something more, and you're not making things worse from a complexity point of view. And as it turns out, if you look at the recent benchmarks, most of the popular results on exact inference is by weighted model counting. It also leads to some interesting changes in the SAT solver, because using a SAT solver naively to do model counting is not that efficient. So you need to do a few other things on top of the SAT solver to make it work. But it can be done. So it leads to some interesting theory as well. Now, you could use weighted model counting as a sub-module in learning, because if you're trying to learn something, like if you're trying to learn a hypothesis or a network, often what you're trying to do is you're trying to compute how likely does this structure capture the data. Okay, so you're computing some kind of condition probability, and every time you have this kind of query, you could use weighted model counting. So there's a whole array of languages and frameworks that try to provide a logic-based solver for doing inference and learning. Again, I'm not going to go into too much details, but this is an area called tractable learning and Bayesian learning, Bayesian logic-based learning. If you're interested, you could always look it up in one of the survey papers to follow up in terms of references. Roland, just a quick question. How much time do I have? Would you say another 20 minutes?
Yeah. I mean, we
Yeah?
started a little bit late, so.
Hmm. Okay, just to keep myself in check. So let's turn to now the second paradigm or the second theme, which is using machine learning for logic. Okay, as I said, this is an age-old problem, because the classical problem that logicians face is, where is all of this knowledge coming from? Encoding expert knowledge into logical formulas is quite a hard task, and you can make mistakes. So it would be nice if you could use machine learning for this. And again, without going into too much detail, there is quite a bit of work in this area. And I would say, to a large extent, they would broadly fall into two kind of meta categories. Okay, one approach is based on entailment. So what happens here is that you have some sort of search space. This could be the space of logic programs, or it could be other representations called tractable representations. I won't go into them, but they are, in very briefly, they are data structures that provide some nice properties from a computational complexity point of view. Okay, so going back to Roland's point, I mean, this could be a very interesting area to get into if you're interested in how complexity theoretic notions can be used in the story on reasoning and learning. Okay. So in the first approach for learning, what you often do is you try to find a hypothesis such that with some background knowledge, you basically get back the data, right? So essentially, you're trying to find a hypothesis that best summarizes the data. That's the idea here. Now, you want to be careful here, because if you think about it, the best representation of the data is the data itself, right? Because what else could capture it completely and exhaustively? But so what you're really trying to do is you're trying to force this H to be quite small, right? The smaller it is, the better it generalizes across the examples, and maybe there is more error as well. So you're trying to somehow balance the fit of this hypothesis given the data. Okay. Another way to look at how exactly you might try to find this hypothesis is that you might have some kind of fitting function. You might have a fitting measure. Okay, so you say, I want to find a hypothesis such that the fit of H to D is better than every H prime given D. Okay, so basically it's the best I can find, which makes sense. But at the same time, this fitting function is proportional to how well the data is captured by the hypothesis, but I want to make sure the hypothesis is not extremely large, because otherwise the best fit for the data, as I said, is the data itself, right? So you're basically penalizing the size of this hypothesis. Does that make sense? So essentially, what you have here is the hypothesis is giving you the examples of the data, but you don't want this hypothesis to be enormously large. Okay, so these are two key paradigms you can explore for learning formulas, and there are variations of this being used in areas like program induction, program learning, structure learning. All of these are essentially approaches for constructing some kind of symbolic structure from data. And they use variations of these equations essentially. Okay. One quick thing I would mention is some work we started to do recently that we're still doing to some extent is this idea that what happens or how could we make it easier if we avoided explicitly constructing this hypothesis? Now, the advantage of learning a hypothesis explicitly is that you have interpretability, right? Because once you've learned the hypothesis, you can look at the hypothesis and you can say, yeah, this is what makes sense. This is what captures the data. But we've been looking at a bunch of approaches. Many of these are motivated by complexity theoretic notions, where we show that by avoiding the explicit construction of a hypothesis, you can get very good guarantees in terms of the correctness of the hypothesis in polynomial time. Okay. Um, there's a paper from NUREPS from 2019 which goes into the detail, and the trick here really is that we keep around many of the data points, and then we use these data points in a kind of a sample effective way to check if any given query is entailed. Okay, so essentially, think of the case where you might have data about the temperature, and then you're asking, is it hot or cold today? And you have a number of readings from the sensor. And what we try to show is that it's possible to sample from this data points effectively, such that you can answer this query in a positive or negative way by not constructing the hypothesis, because constructing the explicit hypothesis is costly. Okay, so there's some work that where we can avoid construction an explicit hypothesis. And if you think about it, a neural network is also constructing the hypothesis somewhat implicitly, right? Because a neural network doesn't give you back a hypothesis that captures the data. So what you're getting in return is some weights on the nodes of the network, and somehow this is capturing the hypothesis. So I think there is something to be said about how implicit learning is quite powerful, and exploring the connections between the logical side and the neural side would be super interesting, I think, for the future. Any questions so far before I turn to the third theme of how logic and learning come together?
Any questions? No, let's move on.
Okay. So the very last thing is where and what can logic do for machine learning? Okay. And this is actually a very non-obvious but highly interesting area of research, because you can use some of the theories we have from logic and apply it to machine learning. Here's just a few topics that we've looked at. So one, as I said, is this idea of constructing tractable representations. So these are all motivated by complexity considerations. And the idea here is that you come up with a data structure inspired by logic that makes both reasoning and learning very efficient. Okay. So there's a whole area of research right now, including numerous workshops at NUREPS and other places that focus on tractable representations. One topic that I very quickly talk about is this idea of regularization, just to give you some detail. But we've also looked at other topics such as abstraction. So essentially, this idea of constructing representations at different levels of granularity. How can you ensure that some representation might be understandable to the data scientist, and a different representation might be more relevant to the manager or the high-level thinker? So thinking about abstraction or coming up with new programming paradigms that can combine reasoning and learning is something we're very interested in. We've done some work on that. And if you're interested, I can provide some references. I'll very quickly talk about a couple of small things here. As I said, I wanted to emphasize one place where logic is being used for deep learning, and this is the idea that you can use logical formulas as regularizers. Okay, so what is this business? So it turns out, as good as neural networks are at a bunch of things, they are often very bad at constraints. So here's a very simple example. Okay, so basically, I have this bounding box, a rectangle, and I want the neural network to only give me samples in this rectangular area. Okay. It turns out if you train a baseline model, no matter how good the convergence is, you get a lot of bad outputs. Okay. So essentially, it doesn't hit into this into these blue rectangles, and it keeps giving you invalid data points. And if you think about something like a robotic setting, this could be very dangerous, right? Because it could try and do actions that could potentially harm someone. Now, if you think about what this is in logic, this is quite a simple exercise. So high school geometry, a student could tell you what these bounding boxes are defined by in terms of the two axes, right? So you could say for x1 values between this and that, and x2 values between this and that, you get the first bounding box and so on. And of course, if you wanted to write this down in logic, it would just be a disjunction over all of these intervals. Okay, so what we want to do is to force these intervals onto the prediction of the network. More precisely, what you really want is that you want to generate samples from this neural network, okay, x0 to xn, such that all of these xi's essentially satisfy this constraint phi. So this is on the right-hand side of this equation, and phi is again this bounding box expression from the previous page. Okay, so the seems simple enough, but it doesn't work. Okay, so as I said, no matter how well you train the network, it keeps giving you a lot of invalid samples, and that's just because it struggles with constraints. Okay, so what we are looking into, and what we looked into, and there's a bunch of different ways of doing this, coming from different groups across the world. Most perhaps best represented by a traffic data set called RODAR from Oxford, where the idea is that you have constraints that capture some of the traffic situations we find ourselves in. Like, for instance, it's impossible that the light is both green and red at the same time. It only has to be one of the following: orange, red, or green. Right. So constraints like this seem simple enough, seem small enough, but if you can't get the network to do this reliably, then it's quite dangerous. So there's a whole bunch of approaches that's been looking at this, and the essential idea here is that basically you add a gate at the end of the output of the network. And as I said, each different approach has a different way of doing this, but roughly the idea is you add this gate, you pass the output of the network during training time through this gate, and every time it gets the output wrong, you penalize the network for getting it wrong. Okay. And it can be shown that by having this kind of loss function that captures this penalization for getting the output wrong, you can get the network to produce samples very reliably. Just to see what this really looks like, this is a plot where you can see the training epochs of a neural network, and you have two models at the bottom. The blue one is completely unaware variational autoencoder, which has not been subjected to any kind of constraint learning. And as you can see, the constraint satisfaction is just a bit better than random, right? A bit better than 50%. So it's not good. Whereas there's one of the other approaches that came to previous to ours is slightly better, but we add this gate at the very end of the output, and this can ensure that we get 100% satisfaction. So this becomes important also when you think about large language models, and you don't want them to utter something that is potentially considered insulting or dangerous. Okay, here's a quick demo of what you could do with this kind of constraint function. So here's a way of training a neural network where we don't really give the labels to the individual images, but instead we simply say that whatever number the first image corresponds to and whatever number the second image corresponds to, when you add them up, you get 7. Okay, so that's essentially the constraint you give to the neural network on training. And you can see that, in fact, the neural network is able to decode each of the individual digits on its own, right? So you can think of this as a scenario in an application where you don't have labels for the individual things, but you have some kind of delayed feedback, and you'd like this constraint to be propagated back into the network so that it understands what it's doing. And there's a way to cross-check whether the network has learned things correctly. Okay, so regularization is a super interesting topic of how exactly you can get networks to produce predictions that satisfy all sorts of constraints. Okay, I'll be very quick in the last slide. I just wanted to talk about a couple of different things that we've been doing. Again, on this regularization aspect, we've been looking at different ways to understand why it works. Okay, so we currently have two approaches, two papers right now that looks at a kind of logical characterization, and another one which is based on information geometry. And we show that this is quite a convincing reason for why the network is obeying these logical constraints. If you're interested, the papers are below. You could have a look to see what's happening there. We've also been doing a bit of work on program induction. I'll give you a quick example of this in the next slide. But we've also been playing with what is called as reward shaping. Okay, so classically in areas of AI such as reinforcement learning, as you know, you have this very complicated matrix that is the reward function. We have been looking at ways in which the rewards could be a logical formula. And then we're trying to understand, does this get us to build agents that are more ethical or more in line with our behavioral constraints? So this is a topic that we're quite interested in. We've also been doing a bit of work on trying to understand the interplay between large language models and how they could improve the performance using logic. Okay. Again, I'll very quickly talk about these program induction and the large language models bit. So in program induction, one of the things we've done is looking at constructing policies, okay, for the RL agent, but which have a logical aspect or logical substrate to it. So what's happening here is that I'm dealing with what is called as a cart pole problem. This is a very popular problem in reinforcement learning. We are trying to balance a pole on your finger. Okay, obviously the pole being long tends to fall off towards the left or the right. And so what you do is you keep moving your finger forward and backward until the pole is balanced perfectly on the finger. And we can show that we can extract a symbolic policy which becomes very readable to the user. So we are able to explain the policy using symbolic languages. Okay. This is a piece of work we did last year with the LLM area. One thing we've been looking at is enhancing what LLMs typically do. So what we have here is a puzzle. Okay, this is often called as a theory of mind puzzle. So often in these situations, you have a bunch of agents in the picture. You can read this if you want, but you don't need to. Essentially, you can think of a card game, right? And in a card game, most of our cards are face down. One of us lifts the card, and maybe I discuss it with my partner and put it back down. And often, what you're trying to work out is who knows what, right? So, or you might have a gossip protocol where people gossip, and you're trying to understand who knows what about whom, right? So obviously, LLMs can't do this by themselves, right? So they're not very good. They get things wrong, and they sometimes if the question is quite tricky, they get things really badly wrong. So what we end up doing is converting the large language model to a symbolic expression. We use what is called as public announcement logic, okay? And then we solve formulas for this public announcement logic exactly using a model checker. We use these responses to again fine tune the LLM. And in the end, we're able to show that we can get fairly accurate performance using the symbolic substrates. Okay, so essentially, what you can see in the top line is the accuracy. If you just focus on the accuracy column, the vanilla model just is a bit better than random, but as you add symbolic substrates, it gets more and more efficient, and you can get exact reasoning as well in certain situations. Okay, so likewise, we've also done some work where we're extending we're extending large language models to do temporal reasoning using a very similar substrate. So we convert the sentence into temporal formulas and then solve it using a symbolic model checker and contrast the responses with the large language model. Okay, so not trying to do everything using LLMs directly, but keeping the symbolic substrate separately because it is more effective and correct. Okay. So just to wrap up, as I said, there are three major branches with multiple aspects to them, discrete and continuous. Roland also mentioned complexity, and these are all interesting angles to explore within the three branches. And the key question we're really trying to work out here is the balance between knowledge provided by an expert versus data. Okay, how much can we get from data? How much knowledge would be useful to not replicate everything in data? And I would say these branches are beneficial for both areas, right? So on the one hand, it's interesting to learn knowledge for logics. This is a problem that logicians have always faced. Adding knowledge to learning makes learning more efficient, requires less data, offers correctness. And finally, if you look at some interesting theoretical questions, you can look at complexity, you can look at efficiency, you can look at verification. So there's a rich set of problems to explore at this intersection. And with that, I thank you for listening. Happy to take any questions. Thank you very much.
Thank you.